Hi, my name is Allison, and I'm the Director of Technical Services at IntelliMagic Inc. In this course, we will be discussing the IBM SVC Architecture as well as performance best practices. The course learning objectives include gain an understanding of the value of virtualization, gain an understanding of virtualization architectures, gain an understanding of the IBM SVC architecture, and gain an understanding of the best practices for each component in the I/O stack. This section contains an overview of the virtualization value proposition. What is the value proposition for virtualization? Reduction in storage management and administration costs. Allowing a core group of administrators to control multiple assets across a distributed storage environment can lead to a significant efficiency improvement. Improved storage utilization. Improved capacity utilization of existing storage assets and control the growth of future spending by as much as 30%. Reduce cost of storage. Capitalize on being able to purchase the lowest cost storage resources behind your virtualization, controlling the growth on average by 20%. And lastly, improved customer and end user availability to data-driven applications. Minimize the downtime associated with migrating data between storage assets. How is this accomplished? Through a single point of storage management for different types of storage, providing the ability to create pools and subsequently tiers to optimize existing storage hardware investments. Ability to migrate and consolidate hardware less disruptively than traditional mechanisms. Reduction in administrative overhead through easy storage management. Advanced copy services functionality independent from storage controller hardware. Potential for improved capacity utilization, both space and performance bandwidth through a balanced approach. And potential for improved performance with large cache and Easy Tier. This section provides an overview of virtualization architectures. There are several types of virtualization architectures. SVC is called an in-band appliance. This means that it resides within the same network or fiber channel path of the host that it connects to, as well as the external storage that it virtualizes. All the command data, as well as the payload data, is sent across the same communication link. The SVC may also contain internal disks, SSDs, that are used to satisfy I/O requests from hosts as well. The IOs traverse the IO path. Any host IO initiated is a request that's either a read or a write. The host driver instructs the host bus adapter to initiate communication with the SVC's fiber channel ports. The connectivity equipment, such as the SAN switches and directors, confirm access and send the packet to the destination fiber ports on the SVC. If the data requested by the host resides within SVC's cache, then the data is sent back across the fabric and to the host. If the data requested by the host does not reside within the SVC's cache, the SVC requests it from the backend storage array. A detailed discussion of the read and write paths for different types of I/O will be discussed in a cache section. Another type of virtualization system is a split path system. With the split path system, the metadata and control data are split out of the path to be processed by the specialized and intelligent device. The architecture relies on intelligent switches that split out the workload from the control data. The advantage is that the load between the virtualization appliances and the storage and host ports does not contain the overhead of the management data. The disadvantage is that the solution is more complicated architecturally. Storage controller virtualization is another type of virtualization. It relies on a storage controller to sit in front of other storage systems and present volumes to the hosts. The Hitachi enterprise systems, such as the USPV, VSP G1000 series, provide this type of virtualization capability, which allows you to group either internal disks into storage pools or external disks into storage pools. All traffic is processed through the virtualization controller. The advantage for environments that heavily rely on an HDS or an existing storage virtualization platform is that they can centrally manage their storage from a single platform. This diagram illustrates the host, fabric, IBM SVC, and backend storage layers. Our focus in this section is on the hosts, how they connect, best practices for connection, and considerations for multipathing. This table summarizes the best practices for attaching hosts to an IBM SVC as it pertains to performance and availability. Use an IBM developed or native multipathing software to configure multiple paths to an I/O group. This will increase the availability by adding more than one path to the storage, and will also provide the performance benefits associated with an increase in bandwidth between the host and the IBM SVC controller. If the multipathing software supports active-active with preferred path, then use it. The only major host platform that does not support this option is VMware. For VMware, use round robin unless it is a stretched cluster. In that case, use fixed path and had the local paths set for the primary volume. Limit the number of host connections to 4. There is additional CPU overhead on the host and SVC when managing more than 4 paths, and there is almost never an additional performance benefit. Do not share HBAs between faster and slower devices, as slower devices can impact the performance of faster devices. Try to configure a single host to a single I/O group. This simplifies management and isolates I/O-intensive workloads. An exception to this practice is when the host has higher performance requirements than a single I/O group can support. When adding new hosts to an I/O group, add it to the I/O group with the lowest amount of workload. When booting from SAN, make sure that the LUN ID is the lowest SCSI ID, 0 for most hosts. Otherwise, your system may not boot. Configure the queue depth different from default, only when it makes sense. In general, don't configure a larger queue depth setting than the SVC node I/O group can handle. In the next few slides, we'll go into more detail on each of these best practices. Multipathing allows a host to have multiple paths to the storage. In this diagram, we illustrate the logical connections from a host with 2 HBAs connecting to a single I/O group. HBA 1 and 2 on the host both have a connection to node 3 and node 4 for a total of 4 paths to the storage. It is the job of the multipathing software to manage these 4 connections between the host and the storage and to present to the host the active paths. In the SVC configuration, there is a preferred path for each host presented vDisk. When multipathing software supports preferred pathing, the IBM SVC node will communicate with the software which paths it should use for which volumes or vDisks. The host will then communicate to the preferred node specified for each volume, which will improve the cache efficiency for access to that specific volume. So what do we do about VMware hosts since they don't support active-active with preferred preference? What we recommend is that you use round robin or VMW_PSP_RR as the multipathing method. What it does is it ensures that the load is balanced across the paths so that the performance on each of the paths is equal. The downside is that it leads to suboptimal cache utilization. The exception to this rule is when you employ stretched clustering. Stretched clustering requires a primary and a secondary site. In those cases, you would want to set the primary volume to have a fixed path so that all of the reads were coming from the primary volume that are local to the host. That way, you don't suffer the performance impacts of reading across a WAN. In a shared HBA configuration, a single host has two 2-port HBAs. Each port is shared with traffic for both disk and tape. While the tape backups are running, there can be significant contention on the ports that are shared, and disk traffic will suffer. This is not a best practice. This setup shows a dedicated HBA configuration consisting of 4 2-port HBAs that are each dedicated to either disk or tape. None of the HBAs or ports are shared between disk and tape. This represents a best practice configuration for managing disk and tape traffic as it isolates the tape traffic to its own HBAs. When assigning hosts to I/O groups, it's important to follow a consistent process that considers performance. This will increase the availability and performance of the environment. The first step in the process is to determine if the host is new or existing. If the host is an existing host, then you don't need to do any host assignment, as the host is already assigned. If it's a new host and you are assigning to a new SVC, then assign to any I/O group. If it is a new host on an existing SVC, then determine which I/O group is the least utilized. The IntelliMagic Vision balance charts are designed to show how well balanced each of the I/O groups is. Configuring queue depth. The intention of this slide is to provide general guidelines when considering queues on hosts. In general, an IBM SVC CG8 node can handle 10,000 concurrent IOPS, but use 7,000 as a conservative estimate. For the DH8, we assume you can roughly double the number of concurrent operations. So, for an I/O group of CG8 nodes, it should be able to handle roughly 14,000 concurrent I/O operations. The average queue depth then, for each host, would be the total number of IOPS, which is 14,000, divided by the number of volumes multiplied by the number of active paths. So using 1,000 volumes as an example and using 2 as a number of active paths by default, you would get an average queue depth of 7 per host to run concurrent operations. Basically, in general, if you have poor response time on a host, but the SVC is not very busy, you can actually try to reduce the queue depth on the host. And if you have good response times on the host, but throughput is low, try increasing the queue depth. This section contains an overview of the best practices for fabric configuration in an IBM SVC environment. In this section, we're going to look at the fabric best practices. This slide summarizes some of those best practices, and we're going to go through each of these cases in a little bit more detail. Really, the key when designing a high-performing fabric is to avoid multiple hops. It's to avoid intra-switch links between high bandwidth hosts and storage. So ideally, you want to keep high bandwidth hosts and storage on the same switch chassis that the SVC is on. You also want to make sure that you have sufficient bandwidth to handle the highest workloads. And you also want to keep some additional ISLs. If you do have to use ISLs, you want to keep some additional spare ISLs available. And we'll go through each of these practices in more detail. In order to improve the availability, it's very important when designing your fabric to have dual fabrics. Each fabric provides connectivity from the host to the SVC. And should one fabric have a failure, the other fabric provides the redundancy required such that the host can still access the SVC. The top picture shows a single fabric with no redundancy. If the switch in fabric A should fail, there would be no way for the host to get to the storage controller or to the SVC. In the case of the bottom picture, we have two fabrics, fabric A and B. Should one fabric fail, there would still be a path through fabric B to the SVC. When designing the fabric with the SVC in mind, it's very important to eliminate ISLs between the SVC and the storage. In this example, we show ISLs between host switches, SVC switches, and the storage switches. This provides too much latency on the SAN fabric and will lead to congestion and potentially major disruptions. It's much better to have the storage systems on the same switch as the SVC. In this example, we show what it would look like in an ideal situation where you would have a large core switch on each of the fabrics and have the SVC, the storage, and any high bandwidth hosts connected directly to the same switch that the SVC and the storage are. In order to optimize the number of paths seen by the host multipath driver, each host HBA port should be put in a separate zone along with two SVC ports, one on each fabric. Do not place more than two SVC ports in a zone with an HBA port, otherwise you'll have more than the optimal number of paths seen from the host by the multipathing driver. The top example shows the correct way of doing this. In the correct way, you have 4 paths total. You can also do it as is shown in the bottom picture, but that presents 8 paths to the host, which is not the ideal situation. So if you have to do it that way, it's possible, but it is preferred to only have 4 paths. This section contains an overview of the best practices for the IBM SVC architecture. An SVC architecture consists of up to 4 I/O groups, each I/O group containing 2 redundant clustered physical nodes. Each of the nodes consists of off-the-shelf Intel processors, memory, and 4 to 12 fiber channel ports. They also support a couple Ethernet ports, and they have the capability of supporting, depending on the model, up to 16 SSD drives. The physical components of the SVCs are commodities. The uniqueness of the SVC is in the software and the logical components. The chart illustrates some of these logical components. Working our way from the bottom of the diagram to the top, at the bottom, we have storage systems. These storage systems externalize LUNs that are seen by the SVC, and they're called managed disks or MDIS. Each MDIS consists of a number of extents of a specified size, default being 1 gigabyte at this point. The MDIS are grouped together to form storage pools. From the storage pools, the extents are then coalesced to form volumes or VDIS. Hosts are zoned to the nodes within an IO group, and the IO groups have access to all the volumes within the storage pools. The volumes are then assigned to the hosts, and the individual components, how they relate to each other, and some of the measurements will be discussed in further sections. This section will cover nodes and ports. The IBM SVC DH8 has several I/O connectivity options. There's several slots, 1 through 6, and in these slots you have to have at least one adapter card. You can have up to 3 8 gigabit per second fiber channel adapters for a total of 12 ports. You could have one 10 gigabit per second Ethernet FCOE adapter with 4 ports, and you can use any of the slots 4 to 6 for the CPU and the compression accelerator and the 32 gig cache upgrade. The IBM DH8 provides up to 12 fiber channel ports per node. IBM recommends that you configure the ports as shown in the table above to optimize the configuration. I'm just going to summarize it by stating that if you have a modest workload without replication, then you can get by with 4 ports. If you have a significant amount of workload but no replication, or modest workload with replication, you need 8 ports. And if you have significant workload and replication, you really need to have 12 ports. IBM SVC allows you to place flash modules within the IBM SVC nodes. On the CG8, you are allowed up to 4 SSDs per node, or 8 SSDs per IO group. There were 2 flavors of the module, 200 and 400, for a total of 3.2 terabyte per IO group. Within the DH8, you can add up to 2 shelves of the flash modules, each shelf containing up to 24 flash drives at 200, 400, or 800 gig each, which is a total of 38.4 terabytes of raw space. The maximum SVC flash capacity is 153.6 terabyte of raw configured across the 4 IO groups, and you can have that configured as RAID 0, 1, 5, 6, or 10. In this section, we'll talk about the best practices for IBM SVC managed disks. There are several rules you should follow when configuring managed disks. First, LUNs should be created to use the entire capacity of a RAID group from which they are formed, as we don't want them to coexist with anyone else on the RAID group. Second, unless using Easy Tier, managed disks need to have the same hardware characteristics or performance will be inconsistent. Finally, LUNs should be the same stripe width, if possible, to ensure consistent performance and extent distribution, though with Easy Tier and auto extent rebalancing, this has become less of an issue. In this slide, we want to look at the best practice of using the entire RAID group. So in the first example on the top, we have 2 RAID groups that feed 2 different MDISks, and those MDISks are part of an MDISK group. In both of those cases, the entire capacity of the RAID groups are used to provide storage to the MDISK. A bad practice would be to split that underlying RAID group up into 2 different volumes. One volume may be being directly attached to a host from the storage system perspective, and one volume being part of an MDISK that's in an MDISK group. What can happen with the MDISK that has contention with another volume from another host? The performance can be inconsistent. And we want all of the MDISks to have the same performance characteristics so that the users get a predictable experience. For the non-hybrid, non-easy tier pools, it's very important to have the same RAID group formatting for the managed volume. In the top example, we see an example where 2 RAID 5 MDISks are created. And in the bottom example, we see where 2 MDISks that are part of the same storage pool are created from different RAID formatting. So RAID 1 has a RAID 5 group, and 1 is from a RAID 10 group. It's not good to mix the RAID formatting because it provides unpredictable results. There are a few other considerations when configuring managed disks. The number of storage systems that provide storage to SVC is limited to 64. This is not usually a problem unless you are using a very small storage controller that scales horizontally. And each time you add storage, it adds a new controller to virtualize. So another one is there is a limitation of 1024 storage pools. This should never really be a limitation. There's also a limit of 128 MDISC per pool. This should not be a limitation either. And there's a maximum of 4,096 MDISC per cluster. And even in the biggest clusters, this should be enough managed disks. When discovering SVC managed disks, it's important to recognize that LUNs are typically shown on their storage controllers in decimal, particularly for the LUN ID. However, when SVC discovers it, it brings it in to the corresponding hex value. So for example, if it was an XIV LUN and it showed as 18 in XIV, it will show as a long list of zeros followed by 12 in SVC. The same is true for storage capacity. Most often the capacity is displayed in decimal on the storage systems, but SVC displays it as binary. Storage pool is a grouping of more than one managed disk. The managed disks are placed in a storage pool, and the extents within the storage pool are used to allocate storage volumes, which are then assigned to hosts. From a measurement perspective, the storage pool is the most critical SVC construct. It provides a single point of relationship with the host volumes as well as the back-end physical devices. So the measurement encompasses the front end and the back end. And in this section, we'll talk about the SVC storage pool best practices. This slide provides a summary of all of the storage pool best practices. Namely, you should not try to utilize managed disks within a pool for more than one storage system. Each storage system should provide managed disks to a single SVC cluster. Each backend RAID group must be included in only one storage pool. For non-XIV systems, consider limiting the number of managed disks between 8 and 12 for DS8000 and V7000. Rather than adding capacity to existing storage pools, consider creating a new pool. Implement striped volumes for all workloads, except 100% sequential, and select an extent size that balances cluster capacity as well as volume granularity. For non-easy tier systems, it's important to only have one storage system per storage pool. Now with the easy tier, you may have a flash system that provides storage, an MDISC, and you may have a standard, maybe a DS8K or an XIV also providing MDISC. But typically, if you're not running easy tier and it's not a hybrid pool, you should only have one storage system per pool. This example shows a bad example on top, which is an EMC and a IBM DS5300, both providing storage to a storage pool. What's bad about this is it's going to provide very inconsistent performance, and what we want to try to do is within a storage pool provide consistent performance. In this example, we show a bad example where a RAID group has been carved into two volumes. Those volumes have been distributed as managed disks to an SVC, and then each one of those volumes, or MDISC, has been applied to different storage pools. Data from a single RAID group should be provisioned as a single volume and provided to just one storage pool. You should have at least 8 managed disks per storage pool. This provides enough MDISC to ensure that there is adequate skew across the managed disks. It also ensures that there are sufficient back-end connections. The size of the extent has a relationship with the maximum capacity in your SVC cluster. While SVC advertises a 32 petabyte cluster support, that would require an 8 gig extent size. The default extent size is 1 gig starting in release 7.1. This seems to be adequate in terms of the granularity and the amount of storage that you can manage, which is 4 petabytes across an SVC cluster. SVC employs cache partitioning to limit the potentially negative effect that a poorly performing storage controller can have on a clustered system. The partition allocation size is defined based on the number of storage pools configured. The design protects against individual controllers overloading and failures from consuming write cache and degrading performance of other storage pools in the clustered system. Consider the rule to be that no single partition can occupy more than its upper limit of cache capacity with write data. These limits are upper limits, and they are the points at which the SVC cache will start to limit the incoming I/O rates for volumes created from the storage pool. If a particular partition reaches this upper limit, the net result is the same as if a global cache resource was full. That is, the host writes will be surfaced on a one-out, one-in basis because the cache destages the writes to the back-end disk. However, only writes targeted at the full partition are limited. All I/O destined for other non-limited storage pools will continue to operate as normal. Read I/O requests for the limited partition will also continue as normal. However, because the SVC is destaging write data at a rate that is obviously greater than the controller can sustain, otherwise the partition wouldn't have reached the upper limit in the first place, the read response times are also likely to be impacted. Let's look at how it works. With one storage pool, the upper limit is 100%. With 2, 66%, 3, 40%, 4, 30%, and then at 5 or more, the upper limit of the cache write partition is 25%. In this section, we'll discuss volumes or VDIS. This slide summarizes the best practices when configuring volumes or VDIS on an SVC. First off, for new volumes, they should go to the least utilized storage pool within the cluster, assuming that those storage pools service the same population. Use striped volumes, even if application or host has its own striping, as long as the stripe sizes are dissimilar. Host LVM striping can actually be beneficial for performance as long as it's more granular than 1 GB extents or whatever your extent size is on the SVC. When you create a thin provision volume, set the cache mode to read-write. This will cache the metadata and improve performance. We'll go in more detail in the next several slides. In addition to the previous slide, there are several other best practices. For example, for non-flash copy thin volumes, the grain size should be set to 256 KB. For flash copy volumes, set the grain size to 64 KB. The default is 32 KB prior to versions 641 and 7101. Set thin disk to auto expand, so if allocated space is used, the disk doesn't go offline if additional writes occur. Use I/O governing cautiously. Throttling to limit the impact of high throughput or high I/O rate applications that are insensitive to response time but may be impacting other applications is a good tool, but it can also have negative consequences. So just make sure you understand what the high volumes are doing. It may be more important that they get optimized or tuned rather than limiting their throughput. If you're using stretched volume mirroring, ensure that the primary volumes are set to the preferred node that is local to the host. Let's look at how different types of I/O operations work for thin provision volume. For a write to an unallocated region, there's a directory lookup that indicates the region is unallocated. Then SVC allocates the space and updates the directory. Then the space is formatted while the data and the directory are written to disk. For a write to an allocated region, there's a directory lookup that indicates that the region is already allocated, and then data is written to disk. For a read to an unallocated region, which is highly unusual, there would be a directory lookup to indicate that the region is unallocated, and then SVC would return a buffer of zeros. For a read to an allocated region, which is the 99.99% chance, there's a directory lookup that indicates the region has been allocated and the data is read from disk. So what is a good idea is to make sure that you enable the caching of the directory metadata so that all of those directory lookups which happen for any of the operations are happening out of cache. In this section, we'll take a look at some of the advanced SVC features, including copy services, Easy Tier, and compression. These are some general guidelines when introducing advanced features. In general, you want to use the SVC to provide the thin provisioning and to also manage the flash copy as well as the DR or replication planning. For one thing, thin provisioning is a chargeable feature on the IBM DS8000, and there's really no benefit to managing it in multiple places. Some systems, for example, EMC with fast VP require thin volumes for configuration, but you can assign thick volumes to the SVC. Over allocation should be done from the SVC alone. There is no sense in trying to manage thin provisioning from multiple places. IBM Easy Tier is designed to move the hottest extents to the fastest drive technology. Normally this is done during a 24-hour period. What happens is Easy Tier collects the data at 5-minute intervals, and this information contains how active the extents are. It then analyzes these I/O statistics and creates a migration plan every 24 hours that optimizes the data layout. Lastly, it migrates the extents to optimize the performance. Easy Tier operates on hybrid storage pools that contain different types of drives, such as SSD or flash, fiber channel, and nearline. Easy Tier planning is based on back-end response times, so read misses are much more heavily weighted on SVC than on DS8000, since SVC does not see much latency on the back-end writes that go to the underlying system cache. So should you run Easy Tier on IBM SVC or on IBM DS8000? Well, it depends on your goal. Do you have multiple controllers behind SVC? Do you want to manage heterogeneous storage environments from a central location? Since SVC supported Easy Tier version 3, there's really no reason anymore to run Easy Tier on the back-end storage. IBM SVC Easy Tier considerations. Easy Tier requires a mix of tiers, so you need at least 2 types of disk technology, either SSD or flash, fiber channel, or SATA. So you need 2 out of the 3. You have to manually specify external MDISks as either SSD or HDD. This requires that you set a tier attribute for the MDISK. If you don't do that, they'll all be the same, considered the same tier by SVC and Easy Tier. Easy Tier is going to improve performance for certain types of workloads, primarily those workloads that are random read miss that have small block sizes. Image mode and sequential volumes are not candidates for Easy Tier, and in order to enable them, you have to configure it both at the storage pool and the volume level. And you also need to make sure you have enough free space in the storage pool to allow Easy Tier to complete the rebalancing work. Remote copy services are provided by SVC and require both bandwidth and distance considerations depending on the recovery point objective. For recovery point objectives of a few seconds, one must use synchronous technology, such as MetroMirror. This is good when distance is less than 5 kilometers and latency is low, as any bandwidth impacts will be felt by all of the hosts at the primary site, or at least any host that's doing write I/O. For distances greater than 5 kilometers, asynchronous copies such as Global Mirror or Global Mirror with change volumes should be used. Typically, Global Mirror is good when the RPO is around 5 minutes or less. In order for the host write response time at the primary site not to be significantly impacted, the bandwidth must be sufficient to handle the highest peaks in the workload. For sites with limited bandwidth, a flexible RPO, and sufficient free space at the primary site, the Global Mirror with change volumes provides a cost-effective means of replicating storage. Keep in mind that regardless of what technology is selected, you need to have the appropriate bandwidth to handle the mirrored foreground write I/O and the background write synchronization. Here are some general guidelines when estimating bandwidth required for remote copy services. Treat MetroMirror more conservative than Global Mirror. Consider peak write workloads and convert to megabits for your network. IntelliMagic Vision does this for you. Include the background sync bandwidth requirements. Make sure to include at least 10 to 20% overhead for bursty activity. Make sure that you include some percentage of growth that reflects the amount of data growth that you're seeing in your environment. And then subtract out some amount for compression. This may be 2-to-1 or 3-to-1, depending on the technology used. Here are some important copy services parameters. At the cluster level, between the primary site and the remote cluster, there's a bandwidth parameter. This specifies the rate at which background write synchronization or resynchronization can be attempted. The GM link tolerance parameter is the amount of time in seconds that a Global Mirror partnership tolerates poor performance of the intercluster link, that is, the link that connects the remote and the primary sites, before adversely affecting the primary write I/O. Ensure you set this to limit the impact of application performance in the case of a link outage. The relationship bandwidth limit. This is the maximum resynchronization limit at the relationship level and also at a volume level. You never want to set this higher than the bandwidth that is available, And you want to set this to a level that's lower than the available bandwidth, such that other activities can also occur. A couple of global mirror and metro mirror errors that are important to keep an eye on, and these will show up in the SVC error logs. The 1720, this indicates that the relationship has stopped. Typical reasons for this are that the link has degraded to such a point where there's an outage. The 1920 error specifies that either global mirror or metro mirror is unable to stay consistent. The typical reasons for this are performance issues, either at the target site or with the link. Global mirror with change volume is a slightly different animal than global mirror or metro mirror. Global mirror with change volumes requires a primary volume, a secondary change volume that stores changes to the primary volume, and then on the remote site, the change volume asynchronously replicates the changes to a secondary target volume. Those volumes are then flash copied to the change volume at the secondary site. In order to optimize the performance at the primary site and balance the throughput, you can use the cycling period in seconds. The default is 5 minutes. So at the beginning of each cycle period, changes in the volumes are replicated to the secondary volume. If the cycle period does not finish in the cycle time, it will run until it does. A longer cycle time, or cycle period in seconds, will actually smooth out the spikes and use the bandwidth more efficiently. So if you can allow for a longer RPO, then a higher cycle time in terms of seconds will allow you to more efficiently use the bandwidth. The way that the RPO works, or the recovery point objective, it can be calculated as the difference between the current time and the last time that there was a freeze. So if the last freeze happened 5 minutes ago, the RPO would be 5 minutes. With the IBM SVC model DH8, compression is now a very viable option. The base hardware does not include real-time compression support. However, you can add additional hardware. There are actually a couple different ways to do this. You can dedicate 8 processor cores to real-time compression with 1 compression accelerator adapter, and this provides you 38 gigs of memory for the compression stack. The other option is to dedicate 8 cores to the RTC with 2 compression accelerators, which actually doubles the bandwidth, and 38 gigs of memory. So it's 32 additional gigs of memory plus 6 from the Spectrum virtualized stack. Note that the second option is required to open the PCIe lanes as well as schedule traffic into and out of the compression accelerator cards. Prior to SVC Firmware 7.3, the sequential prefetch algorithm was overly aggressive, resulting in higher data rates for back-end reads than front-end reads. If you see this on your system, you should consider upgrading to version 7.3.